This talk is more new tricks for defeating SSL in practice. My name is Moxie Marlinspike. And this talk is really the continuation of a story. And so while I hate to repeat myself, I'm going to sort of review some of the things that I've talked about before in terms of tricks for defeating SSL. And hopefully I can kind of get through the review rather quickly, and then we can get on to the new stuff. So I apologize if people have seen some of this stuff before, but I think it's good to put it in context. So in the past, I've talked about basic constraints. And this is a trick from a while ago, and it starts with certificate chaining. The idea is this. Most people think about certificates in terms of coming in pairs, right? So most people think about site certificates, and then they think about CA certificates. They think about the site certificate for whatever entity that's identifying itself, and then a certificate authority that has its own certificate which signs that. But sometimes the picture is a little bit more complicated. You have these certificate chains. So the concept itself makes sense, right? Perhaps you're a certificate authority and you'd like to delegate signing ability to a third party. But the third party doesn't have their certificate embedded in every web browser since 1996. And so what do? You sign the certificate of the third party, which in turn signs, issues certificates for leaf nodes, right? And so this whole thing is presented to a web browser or another SSL implementation, and it's this whole chain, right? There can be more than one intermediate certificate authority. There can be many, in fact. I don't know that there's any RFC or standard which sets a limit. I think it's implementation specific, and I think Firefox, the limit is 25. So you could have 25 of these intermediate certificate authorities in here somewhere. And so the question is, how do we verify these things, right? Someone hands you a certificate chain, what do you do? And almost everyone tells you the same story. The first thing they say is you check the name of the leaf node of the certificate and trying to make sure that that's the same as the name of the site that you're trying to connect to. And then you verify that the leaf node hasn't expired. Then you check its signature. And if the signing certificate is on our list of trusted root certificate authorities, you stop. Otherwise, you move one up the chain and you repeat. So here's an image from IBM's website today. This is basically explaining this process, right? And they laid out just like this, this whole thing. First you, check the first one, and then you just keep repeating up the chain. And so I've said before that I think when looking for security vulnerabilities, a good place to start is a place where developers might not understand the full scope of what's really going on, and yet feel exceptionally clever about the solutions that they implement. So in a situation like this, it's very tempting to use a simple recursive function to validate these certificate chains. And a developer that does so might think, yeah, I used recursion today. It was like elegant, and it was like, we went up the chain and it was the same function and all that stuff. And so when people do that, the emphasis is a focus on the signature validation, right? And the result of sort of a naive attempt at this is that you can validate that a chain is complete, but nothing more. And so this is what I mean by that. Let's say that we have this picture. It's a very, fairly common picture. You have, some certificate authority that signed a couple of intermediate CAs, and eventually I got my leaf node certificate for thoughtcrime.org, a domain that I own legitimately. So what is to stop me from doing this? Creating another certificate for some other domain that I don't own, and then signing it with my certificate, and then presenting the whole chain to some SSL implementation to verify. If you go back and you look at what people say about how you verify these things, we haven't really done anything wrong. All the signatures are valid, nothing's expired, the chain itself is intact, and the root CA is embedded in our browser and trusted. But we just created a certificate for PayPal, and we're not PayPal. So the missing piece is this somewhat obscure field called the basic constraints. And the idea is that not all certificates should be able to be used for all things, right? Some certificates should only be used to identify one entity, like a leaf node, like my domain, right? Those certificates shouldn't be used to sign other certificates. They shouldn't be used for key revocation. There's many things that they shouldn't be used for. And so there's this field that basically specifies what a certificate is allowed to do. The trouble is that back in the day, most certificate authorities would issue certificates just without this field. It would just be absent entirely. And you would think that if you were like a SSL implementation and you were verifying a certificate, you would assume the conservative thing where if the field is just absent, it's not a certificate authority. But in reality, whether the field was there or not, many SSL implementations didn't bother to check it. And so the upshot of this was that anyone with a valid leaf node certificate could create and sign a leaf node certificate for any other domain. Essentially, your random leaf node certificate was a certificate authority. And when presented with the complete chain, Internet Explorer, Outlook, Conqueror, OpenSSL, many others, all considered it to be valid. So one day, Microsoft did something particularly annoying, and I blew this up by publishing it. Microsoft claimed that this was, a real vulnerability, but it's basically impossible to exploit. So I published the tool that exploits it. And the tool was called SSL-sniff. Sorry. So imagine you have this picture. A client's trying to connect to a server over SSL. SSL-sniff performs a man-in-the-middle attack, where it intercepts the client's connection and generates a certificate for the site that the client is trying to connect to on the fly, and it signs it with any random valid leaf node certificate you have and passes the whole thing back to the client. The client validates the certificate chain using these pictures and diagrams that everyone says you're supposed to do. And simultaneously, SSL-sniff makes a totally normal, valid SSL connection to the server. And then you just pass data back and forth from the client to the server. The important thing is that in the middle, where SSL-sniff has the data, it is in the clear. So you can log it or modify it or do whatever you want. So the question, sort of moving forward now, is this thing still useful, this tool? Post-disclosure, this was a while ago. Post-disclosure, is this still useful? What can we do with it? So first, I'd say that you'd be surprised who still doesn't check basic constraints. Second, for a long time, this was still useful because in the context of the web, even when people were presented with warning dialogues in browsers that had been fixed, most of the time they just clicked through them. And there's actually like some kind of cool stuff that you could do where like a lot of web browsers would start validating a certificate chain, and as soon as they encountered an error, they would stop and throw up a dialog that's like, oh, we found there's an error, this is it. And so like the second thing that they do is check the timestamp, like the validity, to see whether it's expired or not. So what you could do is like on the fly, create a certificate with like, a bad signature, but expired 10 minutes ago or something. And so like a web browser would see that and it would pop up this dialog that would be like, something is wrong. This expired 10 minutes ago. And most people would look at it and be like, well, it only expired 10 minutes ago. It's probably still okay, whatever. And they would just click through it, which is, not very elegant, but effective, right? And then, so this thing is still sort of useful as a general tool for man-in-the-middle attacks, right? Like the folks who did the MD5 hash collision stuff used this to deploy their attack once they'd gotten their rogue CA cert, because it does exactly what you want. Once you have a CA certificate, the thing is you've still got to, create the certificates that you're trying to spoof, and this thing will do it on the fly, right? It intercepts a connection, generates the certificate, signs it with the CA cert, and passes it back. And so there are other uses yet, which I've been hinting at for a while. Some to be disclosed another day, and some to be disclosed today. More lately, I've been talking about SSL stripping. I've been talking about this for a little while now, so I'll try to be brief. But SSL stripping is about bridges. The thing is that SSL can be useful, but how it's deployed really matters. And sort of the thesis of this SSL stripping attack is that on the web, SSL is almost never encountered directly, right? No one types https:// into their web browser, right? SSL is encountered either through a 302 redirect, like you type bankofamerica.com into your browser bar, and it makes an HTTP request to bankofamerica.com, which sends back a 302 redirect that says, hello, please connect to https:// bankofamerica.com. And eventually, the user ends up at an SSL secured page. Or SSL is encountered through links, right? You're browsing along, and eventually you encounter a link that says, check out, or my shopping cart, or log in. And at that point, you are, switch into SSL mode. The thing is that both of these points are bridges, and they're weak, right? Because they're dependent on HTTP. And so the thesis of SSL stripping is that you can essentially attack SSL before you even get there. You know that in the past, SSL sniff has focused on doing man-in-the-middle attacks against SSL connections themselves, right? Like you want to intercept the actual SSL connection and perform some kind of man-in-the-middle attack. But when you start thinking about the way that SSL is actually used on the web, you can perform your attack before you even get there. SSL strip is another tool that I have, and it performs man-in-the-middle attacks on the HTTP connections themselves. So the deal is that you start watching HTTP traffic go by, and as it's going by, you watch for links to to SSL encrypted pages. And you also watch for the location headers. These are the things that are going to be in the 302 redirects that eventually upgrade you to SSL. So these are the two bridges that we've been talking about, right? So you watch for these two things, and whenever you see them, you just swap them for identical HTTP lookalikes, and you keep a map of what you've changed. Then you continue to watch the HTTP traffic go by, and whenever you see an HTTP request for a URL that you've stripped, like a URL that should be SSL protected, but you've downgraded it, instead of proxying that out as HTTP, you go ahead and proxy that out as HTTPS to the server, right? And then you watch the HTTPS traffic come back from the server, and you keep a map of all the relative links, the CSS links, the JavaScript links, all that stuff, because those are all relative to what would be SSL encrypted pages. So, the upshot of, sorry, I'll go back. So the upshot of this is that the server never knows anything's wrong, right? It's getting SSL requests for the URLs that it wants to be SSL protected. And the client never really displays any of the disastrous warnings that we want to try and avoid. There's no dialogue that says something's wrong. Nothing gets rendered out in any of the pages that says something is amiss, right? The only thing that's different is it's missing some of the positive feedback, some of the positive indicators like, the little lock icon and stuff like that. But I feel like those things have been sort of toned down anyway, that there's been more of an emphasis on negative feedback lately. And so I think most people's usage pattern is that they just sort of browse along until there's something that tells them that there's something wrong. So how does this look, right? So this is like a secure page. This is Gmail's login. So this is the secure version, and this is the strip version. It's pretty subtle. Some of the indicators disappear, but there aren't that many left, really, and none of the no warnings, no dialogues, nothing telling you that anything's wrong. This is Safari, so this is the secure page. This is the strip page. If you go back, the only thing that's different is the little blind embossed lock icon in the top right. That's the only thing that disappears, and the S, I guess, and the HTTPS. Right. And so this sort of evolution of where the positive and negative feedback in browsers have been going really helps this attack. So anyway, that's a very brief overview of SSL stripping, and I've talked a lot more about it in the past, and it's that thesis of attacking that bridge between HTTP and HTTPS is really just a starting point. There's a whole ecosystem of directions that you can go from there. One thing that I pointed out in the past is you can adapt homograph attacks to work in this situation, and which can be deadly. So I'm not doing it justice, but the question is, and so I guess what I'd say is this attack continues to be deadly in practice, that it remains highly effective. But the question is, where can we go from here, right? And this is the new things, right? And the question for me is, where do we need to go from here, right? The thing is that this is deadly in most sort of web browsing situations, but the thing that it doesn't Where it falls short are places where people now tend to use bookmarks for like HTTPS, HTTPS bookmarks, and then also other SSL protected protocols like, IMAP, POP3, SMTP. These protocols don't expose a bridge between a secure and insecure protocol and don't give us an opportunity to perform these kind of attacks. So what we really like are some tricks that can get us into those places, right? And so let's think about that. So what's with certificates anyways, right? People always talk about certificates, but what really are they? They're actually these pretty simple structures. The basic idea is that a certificate is supposed to identify a subject and communicate a subject's public key. The certificate is known to be valid because it's provided by some issuer who is thought to be trusted, and it's signed with their key to let you know that everything is valid. This is what a certificate looks like if you dump it in OpenSSL or whatever. This is like Google's certificate, and you can see that it identifies Google and it's issued by Thought and it has their public key in it and there's a signature so that you know that the certificate is valid. So ultimately, when designing a secure protocol, the three things that you're after are secrecy, authenticity, and integrity. You need all three. People talk about secrecy a lot, and when people think about encryption, they're usually just thinking about secrecy. But if you don't have authenticity and integrity, you really have nothing at all, and we'll see why. So the basic kind of SSL handshake beginning looks like this. You have some client, it wants to connect to a server, maybe it wants to connect to paypal.com, and it sends a message to the server that says, hello, I am a client, I support SSL version whatever. These are the cipher suites that I support. I like these compression methods. Here's a random number, a few other things. And the server responds by saying, yes, hello, I am the server. I also support SSL version whatever. I think we should use this cipher suite and this compression method that you've told me you support. And by the way, here's my certificate. Now, when the client gets the certificate, the first thing it's going to do is look at that subject field, right? And it's going to compare it to whatever it's trying to connect to, right? So if you typed paypal.com in your URL bar, or something in your IMAP server settings, or something in your IRC server settings, the first thing it's going to do is check the subject of the certificate that it receives against whatever is in this thing that you entered to make sure that you're actually connecting to the thing that you want to connect to. This is to provide authenticity. And this really is where the problems for us begin as attackers, right? Because we can do a man-in-the-middle attack and intercept the client hello. I mean, we can intercept that no problem, and we can send back our own server hello that says, yes, I am a server, I support whatever, But we've got to send a certificate. And what do we send, We can't just send, the actual server certificate because it has a public key embedded in it that we don't have the corresponding private key for, so, we wouldn't be able to decrypt anything that's encrypted to it. So this is really where the problems for us begin. So we need to think about that. And let's start by looking back into the past again. So in 2000 or the late 90s when I was getting certificates for this basic constraints vulnerability, really all I needed to do was get an SSL certificate for a site that I owned, right? And back then things were different. There were actual notaries involved. There were, I had to present state ID. I had to make phone calls. There were real people that I talked to on the phone. I remember talking to some guy at VeriSign on the phone, and he was grilling me. And I remember thinking to myself, my God, how am I going to prove to this guy that I am me? It was an intense process. That is a bygone era. These days, it's all about online domain validation, right? So this whole process has been replaced by a website. So you go to this website, Thought, VeriSign, whoever, there's a million resellers now, and you paste in your certificate signing request. Certificate signing request is another simple structure, and it's defined in the standard PKCS number 10, and it looks like this. Again, there's a version, there's a subject, the subject is you, your public key, whatever attributes you want to include. And so here is, again, our old friend, the subject. This is the thing that eventually makes it into the certificate that is issued to you, this exact entity, right? And so let's say that I submit a certificate signing request for bankofamerica.com, right? www.bankofamerica.com, right? So any certificate authority is going to look at the root domain here, do a whois lookup, and pull out the administrative contact information for that domain. Then it's going to contact them by email or by phone or something and send them a token, which they have to respond with to prove that they are really them, that you are really authorized to be getting a certificate for this domain. The important thing is that they only look at the root of the domain, right? This is where the contact information is in the whois database. They don't give a shit about the subdomains, right? Subdomain could be anything, right? It could be certificate authorities are a total ripoff, .bankofamerica.com, right? They don't care. If you submit that, they will dutifully look at the root domain, do the lookup, and contact the people. There's no person involved. There's nobody to be offended here, right? Okay. So I'm oversimplifying the picture a little bit. The subject is really not just an ASCII string. It's actually this whole other structure called a distinguished name. To understand that, you have to understand that the X509 standard is a total nightmare. There's been 3 revisions. It's 20 years old. Parts of the standard have literally been lost and then found again. I'm not kidding. When I think it was the 1988 standard was being updated to the 1991 standard, whoever was just like cutting and pasting the stuff over just forgot to like cut part of the standard over and paste it in to the new thing. And then they published that as the standard. And then people implemented the standard based on the thing that was like left out. And then later they figured out, oh, we forgot that part of the standard. And they found it again from the old one and they re-included it as the new standard, but it's really the same standard. And so there's this whole thing where it's like, you're supposed to do this, but really remember they forgot part of it that time when it was published. So a lot of people do this differently. So what you do is you get the thing and then you check this, but if that doesn't work, you check this other thing. And you're not actually supposed to have done that, but it's a nightmare. The original sort of vision for this distinguished name was that each distinguished name would fit into this like global directory information tree, right? So, for me, I would have a certificate, and the country would be USA, state would be Pennsylvania, locale would be Pittsburgh, organization would be Institute for Disruptive Studies, organizational unit would be Research and Development, common name would be Moxie Marlinspike, right? So it's this hierarchical thing that uniquely identifies me, right? In practice, most people get to locale and say, what the fuck is locale? And just like type something weird in there. And anyway, the whole thing totally broke down, and the sort of global DIT never really materialized. One of my favorite quotes is from this guy who was implementing X509. He says, "There's nothing in any of these standards that would prevent me from including a 1 gigabit MPEG movie of me playing with my cat as one of the RDN components of the distinguished name in my certificate." And the thing is, he's right. So this DIT never materialized or whatever, and particularly when we're talking about SSL, the convention is to just sort of ignore most of the distinguished name. Most SSL implementations don't care what any of the distinguished name fields say. They only look at the common name. And the convention is that in the common name, you put your domain, right? So whatever domain you're trying to identify with this certificate. So this is where www.bankofamerica.com would be, right? What is a common name, right? It's, X509 is an ASN1 formatted deal. So this is the ASN1 format for the common name field. And, it's straightforward. There's like a sequence that identifies this as a common name. And then there's a string type that actually holds the value. And X509 supports many different string types, but the simplest version is something like an ASCII string, an IA5 string. And so an IA5 string is formatted like this, where there's a single byte, 0x16, that identifies it as an IA5 string. And then there's a 1 byte length. And that length field specifies the length of the string to follow. And then there's the actual string, 1 byte per character. So if you had a string that it was just called, the string contained the the string value, it would look like this. You'd have 0x16, 0x5, because it's 5 characters long, and then you'd have the ASCII representations of each character. Pretty straightforward. The important thing to note is that common names are essentially Pascal strings, right? If people remember how Pascal stored strings in memory, there would be some number of bytes that prepended the string that specified how long the string was going to be to follow, and followed by the actual string data. So in memory, it would look like this. There's a 1-byte field that determines the length, and then the actual characters that followed. This is different from how C strings are represented. So if you have a C string, you have like a string that you get a pointer to just the first character in the string, and you have no idea how long it is, and you need to continue walking through each character in the string until you encounter a null character, and the null character indicates that you've reached the end of the string. So there are 2 different models. I always kind of like the Pascal strings, but so anyway, well, hold on. Let me just say that one critical difference here is that if you're dealing with a Pascal string, a null character has no special meaning, right? It's just another character in your character string. It's not imbued with any special meaning at all, which is very different from a null character in a C string. It has a very specific purpose, right? So we want to submit this certificate signing request to a certificate authority, and we want to have it signed. We have to put something in the common name field. Ideally, we'd like to have www.paypal.com in the common name field so that we could intercept communication for PayPal. The problem is that we don't own paypal.com and are not listed in the Whois database, so they're going to contact someone else when we submit this thing, and they'll probably say, no, we didn't ask for a certificate or whatever. But we do own, or at least I own, thoughtcrime.org, right? So I could get a certificate for thoughtcrime.org. I could and also get a certificate for www.thoughtcrime.org. And remember that they don't care what the subdomain is. They only look at the root domain. They look at the root domain, thoughtcrime.org, get the Whois information, and contact me, right? So it could be www.thoughtcrime.org. It could be verisigneatschildren.thoughtcrime.org. It could be something totally nonsensical. It doesn't even have to exist, I.thoughtcrime.org. It could even be www.paypal.com null character.thoughtcrime.org. If I submit this to a certificate authority, they will look at the root domain, thoughtcrime.org, do the Whois lookup, and contact me. So now we could try using this in our man-in-the-middle attack, right? So the client sends a client hello. We say, yes, hello, I'm the server. I support these protocol versions and these cipher suites or whatever. And here's my certificate, www.paypal.com null character.thoughtcrime.org. Wow, why would I even be on the wireless network? Right. So when I present this to a client, the first thing that they're going to do is check the subject. If someone typed paypal.com into the URL bar of their browser, they're going to want to compare that to the subject in the certificate that I just sent them, right? And so that code might look like this. Char star destination equals get domain that we connected to. Char star common name is get common name from certificate. And if everything is okay, stir comp destination and common name will equal 0. These will be the same strings, right? That code will work like this. Destination will be the destination you're trying to connect to. Common name will be the value of the certificate, and you'll have a pointer to the first character of each one of these values. Stir comp will look at the first 2 characters and check to see if they're the same. If they are, it will continue to the next character until it reaches the end of the string, denoted by the null character. When it reaches the null character, it will think, I've reached the end of the string, these are the same, and return success. So, in the eyes of most SSL implementations, this certificate is completely valid for www.paypal.com. No. So what are most SSL implementations, right? Web browsers. Firefox is vulnerable, Internet Explorer is vulnerable, Chrome, Lynx, curl. Mail clients, Thunderbird, Outlook, Evolution, chat clients, Pigeon, AIM, IRSSI, Center ICQ, the SSL VPNs, AEP, Citrix, I don't even know what other ones there are. These are all vulnerable to this attack. So it looks like this. I have a new version of SSL-sniff, SSL-sniff 0.6. And this is sort of like, you can imagine, the first cut of the new version, right? So again, SSL-sniff performs a man-in-the-middle attack, and it checks to see what the client is trying to connect to. And if you have a null prefix attack certificate for that server, it will perform the man-in-the-middle attack. Otherwise, it'll just let the connection go through. So how does it look? We looked at SSL-strip and saw what the difference is between how a page looked when it had been attacked before and after SSL-strip. So this is like a valid, this is a non-man-in-the-middle page for Gmail's login. This is the attacked version. Show it to you again. Normal version, attacked version. There is no visible difference. Even if the user were to try and inspect the actual certificate, when they click on the thing, of course it's going to display the value of the certificate, right? And when it displays it as a C string. So even if you look at it, the value is correct. Even if you open the next one with the view certificate thing and actual look at the field, it looks correct. It's sort of invisible to the user. So what are some disadvantages to this attack, right? First, I think targeted attacks are kind of lame. I don't want to have to get a certificate for every site that I want to try and attack. I think phishing is just too much work. You don't want to have to get the one thing and then get everyone to go to the page that you want them to go to. Most of the time, you want to man in the middle an entire network and just get everything on the network. You don't even know what you want to attack a lot of the time. You don't want to have to prepare for that. You just want to get whatever anyone's doing, and sometimes it'll be useful. So let's think about that, right? So maybe the first thing that we would do is look at the source code that an implementation like NSS, which is what Firefox and a bunch of other clients use, and see how they're comparing these things, right? So we can look at the source code, and don't look at it too carefully. Let your eyes go out of focus. Just look at the shape of it. All these nested things, it just goes out, and it's too long for one function. I mean, this goes on for 4 pages, right? Without even looking at a single line, you can look at a function like this and know there's a bug in here somewhere. Seriously. So then your eyes start to clear. And you look at the first line. Register int xy. Register? How old? Compilers have been ignoring register shadowing for 10 years. So that's another clue that something might be up, right? So then you continue looking through the code, and you find the wildcard matching, right? And you look at it closely, and it seems kind of weirdly inefficient, and then you look at it some more, and you realize that you could get a certificate for star nullcharacter.thoughtcrime.org. You have to shell out a little extra because it's a wildcard certificate, but it's worth it, right? So you get this certificate, and it will match any domain that you're trying to connect to. It's actually better than a CA cert, because if you get a CA cert, you at least have to sign, you have to create and sign another certificate to then present for whatever they're trying to connect to or whatever. This, you just hand them the same thing over and over again. You don't even have to sign anything. It's thing. And then there's other weird stuff in there too. If you don't want to use a null character for some reason, you could get star tilde.thoughtcrime.org, and that would match too. There's all kinds of stuff. It supports grouping. So if you don't want to shell out for the wildcard certificate because it's a little extra, you could just think of all the things that you might want to attack and just get one certificate that's paypal.com or mail.google.com or etrade.com or bankofamerica.com or whatever. Yeah, I don't know if there's a limit, but nullcharacter.thoughtcrime.org. And of course, there is a remote exploit in there. If you look at how the grouping works, they do a memory copy, and they allocate based on the length of the string, and that function is going to be based on where the null character is in the string. And then they run through the string again, looking for a closed parenthesis, ignoring wherever the null character might be, and then they happily copy from the beginning of the string until they reach the closed parenthesis. So, you could have a certificate that looks like this. They will allocate this much memory and copy this much memory. This is an interesting exploit, actually, because the star is actually aligned to make this exploitable, and which there are a lot of things in there where it's you keep looking at it and you're like, oh, okay, but there's no way that you could get shellcode past the thing, the Unicode filters or whatever, and then you look and you're like, no, actually you can get the shellcode past the, and that, and it's like, oh, but they do a stir dupe before, so they strip this off, and then you're like, oh no, but then the tilde becomes a null character later, so yeah, it just shouldn't have worked, and it did. Anyway. The other kind of cool thing about this is that you don't even have to get this signed to exploit it, right? Because when the browser gets the certificate, it'll check all the fields to make sure to compile the full list of errors to prevent that attack that I was talking about before, where it gets to the timestamp and stops. Now they check everything, and so even if the signature is bad, they'll go to check the name, and bam. So this does yield something exploitable. Okay, so the next version of our SSL sniff now has wildcard support. So it does the man-in-the-middle attack on the network, or if it doesn't have a null prefix attack certificate for NSS clients, it will just pass them the universal wildcard certificate. So at this point, SSL sniff has to start fingerprinting the network, right? Because you want to start identifying what clients you want to attack in what way. So it fingerprints the networks to figure out what clients are what, and then basically every NSS client is intercepted. And all the non-NSS clients that are vulnerable are intercepted if you have the null prefix attack certificate. And then whatever non-vulnerable clients there are just sort of left alone. So no one can detect it, So what do we have to worry about? Not really. What time is this over? 3 o'clock. All right. What do we have to worry about? The two things that I think we have to worry about as attackers here are certificate revocation and updates, right? So first, it would be unfortunate if some bitter certificate authority audited their stuff and figured out that they had wanted to revoke some of these wildcard certificates. And also, it would be unfortunate if SSL implementations fixed their stuff and updated their software. We wouldn't be able to exploit them anymore, right? So let's start with certificate revocation. Okay, so these days it's all about Online Certificate Status Protocol, OCSP. The deal is that it's a changing world. There are more and more certificate authorities. More and more potentially fraudulent certificates are issued, or there are more and more certificates that are compromised and need to be revoked. And the old model of maintaining these long certificate revocation lists that are then sort of infrequently updated, and there's one for every certificate authority and all this stuff, wasn't really working. And so now there's this new protocol, OCSP. And the deal is it's supposed to be this lightweight sort of online protocol, right? So whenever an SSL stack sees a new certificate, something that it hasn't encountered recently, it will make a quick request to the OCSP URL that's embedded in the certificate and ask the certificate authority, hey, is this thing still valid? Is this okay? Has it been revoked, And the SSL stack receives a signed response from the OCSP provider and is told whether it's been revoked or not. So as an attacker, this is deadly, right? If we're forging certificates and they get revoked, then pretty quickly everyone's going to start to notice, right? Because these browsers are going to do these online checks as soon as they see them, and they're not going to be considered valid. So that's a big problem. And you can see, here's a certificate. This is, again, Google certificate, and there's the OCSP URL that's embedded in the certificate, ocsp.thought.com, right? So if we ever, somehow compromise the private key for this certificate, they would just contact Thought and say, hey, please revoke this thing. And Thought would immediately start responding to the OCSP responses saying, don't accept the certificate. And all sort of modern web browsers and SSL stacks would immediately revoke it. And that would be a problem for us. So let's look at OCSP. The basic OCSP response looks like this. There's a status, just sort of a 1 byte value. And then these response bytes that detail whatever's going on in the status. And the response bytes are actually optional. You only have to include them depending on what the status is. The response bytes look like this. So you have another structure, and there's the actual response data, which is sort of telling you exactly what's going on, and then a signature. And the signature comes from the certificate authority, right? So that's a problem. If we want to forge an OCSP response, we might have difficulty forging the signature on the certificate, right? But the interesting thing about this signature is that it doesn't cover everything. It only covers the response data. Notably, it doesn't cover all this other stuff. including the response status. So what's up with response status? All right, the response status looks like this. It's a 1-byte value, and these are your possible values, right? Okay, so we got to decide if we're going to forge this. We got to send something back, right? So successful. Well, we'd like to send that back, but we can't really do that easily, because if we do that, we're supposed to include the optional response data, and that has a signature in it that we then have to mess with. So we don't really want to send back successful. Okay, malformed request. We wouldn't have to include the response data, but that doesn't sound that good. Malformed just, leaves you with a bad feeling. Internal error. Again, we probably don't want to send that one because it includes the word error, and that probably doesn't sound good. And then you find try later. That doesn't sound bad at all. It's not really implying that anything is wrong. Particularly, there's nothing wrong with the certificate that you issued or that you're issuing the request about. It's just saying, hey, try back later. It's almost implying that it could be successful at a later time, right? So it turns out that if you want to send the try later thing, you don't have to include the response bytes. So your OCSP response looks like this. You just include the response status, which is literally 1 byte. That is literally the ASCII character 3, 0x33. That's literally all you have to send back. And it turns out that every SSL implementation that I've tested agrees that it doesn't sound so bad. And so if they get a try later response, they just assume that it's successful and continue. So what that essentially means is that this entire standard, the OCSP standard, can be defeated by the number 3. Right. So now our new version of SSL Sniff is OCSP aware. So you run it and you give it some command line arguments, and it watches the network, fingerprints the clients that it wants to attack or whatever, and then it does the null prefix attack, or it uses your universal wildcard certificate. And if it sees any OCSP requests for any of the certificates that you have in your certificate store, it just sends back 3. And you've defeated any certificate revocation that might be going on. Okay. What's the other thing we have to worry about? Updates, right? So it used to be that people downloaded software. And it's a changing world. Software is becoming more and more complicated. The stakes are higher. Bugs that appear in software tend to linger for a long time, and so it seems like a good idea to try and implement some mechanism that will update the software more quickly. And so a lot of software has been deployed with this auto-updating feature, these things that self-update. And the problems get fixed a little bit more rapidly. So for attackers, that's kind of bad news. Just by sort of standing here, talking to you, it means that there's some probability that these things are going to be fixed relatively recently, or relatively soon. But it does seem like the update mechanisms themselves can be kind of a bad idea, right? You have software that's connecting somewhere on the internet and downloading other software and running it. So maybe there's something that we can do with this to solve our problem. Okay, so if you look at Firefox and Thunderbird, any of the Mozilla products, when you install Firefox, it comes with a feature called Automatic Update Service that in my experience is enabled by default. And this can be trouble. The Automatic Update Service works like this. A client connects to the update server in the sky, aus2.mozilla.org, and it uses a TLS connection, it uses an SSL connection. And it says, hello, I am this product. Do you have any updates for me? Here is my product, my version number, my build ID, my OS, my locale, all that stuff. So it would say, I'm Firefox version 3.0.12, build ID whatever, OS Linux, locale, and US, channel stable. And the update server in the sky responds, yes, as a matter of fact, I do. Here is a totally unsigned blob of data. run it. The problem is that Firefox and Thunderbird depend on their TLS connections to the update server to defend them against all possible attacks. So if you can compromise the SSL connection, you can send back whatever data you want. The code that's returned from the update server is either just a binary diff against whatever version you happen to be running, or it's just a complete image of whatever binary they want you to run. And in my experience, by default, the minor updates are just sort of downloaded and installed silently. Like if it's a minor update, it just sort of downloads it, installs it, and next time you restart, it's running. And it'll say, we just installed a new update, it's running now, or whatever. And like the major version updates it will like tell you, hey, there's a major version, do you want to install or whatever, you know? But the thing is that the update server is the thing that reports the version number, right? So the update server is the thing that essentially decides whether code is installed silently or not. And as attackers, we can become the update server. So this is a problem, right? Because as vendors start to release patches for this vulnerability, the update mechanisms themselves are going to be vulnerable. They're going to be targets, right? That if it's announced, hey, there's a new version of Firefox, everyone is going to assume that like their updates are going to start rolling in or whatever. But there's no way to know whether these are the real updates or someone sending them false updates. All we need is either our single universal wildcard cert that will work for everything, or if we don't want to shell out for the wildcard cert, we can just get a null termination prefix attack cert for aus2.mozilla.org, and we can take control of the update mechanism. So we can send back anything. We can send back a rootkit that logs keystrokes. We can send back something that sends all the traffic through a server of our choosing, a completely legitimate image that just happens to include our own CA certs for future use. Or just to be confusing, you could send back a totally different web browser. You get updated and it's like, thank you for upgrading to Galleon 0.0.3, you know? Or it could just, you know, Notepad could just start up, you know? And this also works for add-ons, right? Like, it's not just the image itself, but also all the Firefox extensions that you have running. Periodically query addons.mozilla.org using an SSL channel and say, hey, are there any updates for me? And so here we can intercept the add-ons updates as well. I had taught a training yesterday, and at the end we had like a little like malware competition to see who could write the best update to exploit this. And I guess the winning one was one that installs, you know, as your add-on or whatever, and then it just sends from now on, anywhere you are, anytime you post data to a form, it sends it to you too, you know? So it's kind of like the man in the middle attack that keeps on giving, whatever, you know? Right. So the problem is that in order to patch your system effectively, you are not able to trust anything that comes through automatic updates. And at this point, especially if you've been here on the wireless network, you can't trust anything that has ever come through the automatic updates, including add-ons, right? So now we have a update-aware SSL sniff, right? So SSL sniff, same as before, does all the same stuff, except every NSS client's communication is intercepted. All the non-NSS clients that are vulnerable are intercepted. We deny OCSP, and we watch for update polls and respond with a custom build that you can specify, or a custom add-on that you can specify, if you so choose. Okay. So just to mention, stripping null characters is not a solution to this problem, right? So there's like two SSL implementations that are not vulnerable to this attack directly, Safari and Opera. And I haven't tested this very intensely, but it appears that they just strip the null character from the common name strings before they're compared, which is problematic. So basically, the way it works is that if we have our null prefix certificate www.paypal.com nullcharacter.thoughtcrime.org, it will become www.paypal.com.thoughtcrime.org when they do the compare, right? So that won't match www.paypal.com. So it does actually defeat this attack, right? But it's not a good solution because they're just vulnerable to a different attack. And it looks like this. All right, so something that's weird about this vulnerability is that sometimes the certificate authorities are vulnerable to it themselves. So like internally, when the certificate authority goes to do the check and like parse out the root domain of the thing, they will get tripped up by this vulnerability, and like the null character will confuse them. So like for some certificate authorities, if you present www.paypal.com null character.thoughtcrime.org, they will internally validate it as www.paypal.com. So they'll try and send an email to www.paypal.com. But the thing is that if they do send an email to www.paypal.com and those people say, hey, everything's cool, what will eventually end up in the certificate that's issued to you is the entire original subject. So www.paypal.com null character.thoughtcrime.org is what will end up in the certificate. So normally this isn't very useful to us, right? Because if we could authenticate for paypal.com, we could just get a certificate that says paypal.com. But there's like cool things you could do, right? You could register a domain like sitekey.ba. And then you get a certificate from one of these certificate authorities that's sort of internally vulnerable for sitekey.ba null character inc of America.com. And so if a CA is internally vulnerable to this, they'll validate it against sitekey.ba, which we own. And then it will later end up in the certificate as sitekey.ba null character inc.bankofamerica.com or whatever. And then when it's presented to like Safari, they strip out the null character. And so the thing becomes sitekey.bankofamerica.com. And now we can perform man-in-the-middle attacks against sitekey.bankofamerica.com, which is where you post your login credentials. So, sort of in conclusion here, we have a man-in-the-middle attack that will intercept communication for almost all SSL and TLS implementations. In the case of NSS, which is what Firefox, Thunderbird, Evolution, AIM, Pigeon use, we only need a single certificate. And we've defeated OCSP as it's implemented everywhere. And we've hijacked the Mozilla auto updates for both applications and extensions. And we've got an exploitable overflow. So in short, we've got your passwords, your communication, and control over the software that runs on your computer. Thank you. So on my website right now is the old version of SSL Sniff that doesn't support these new attacks. And SSL-strip has been available for a while. Anyone can get it there. And at some point, I will put the new version online as well. Oh, right, the questions thing. Anyone have any questions, comments, thoughts? All right, yeah, go for it. Right, yeah. Like most man-in-the-middle attacks, I think client certificates will probably stymie this thing. The question is, how are the client certificates authenticated, and are they also vulnerable to these null prefix attacks? Yeah. You and then you. I can't hear you. Oh, I don't know. Yeah. Yeah. I can't hear you. Is there like a microphone that the question people can use? Yeah. Yeah. Well, we've got some time, so maybe if we just like wait a second, the loud people will stop being loud. And okay. Yeah, go for it. Okay. So the question is, what about EV certs? So the answer is like, these certificates that I'm getting are not EV certs or whatever, so they'll be presented to the client or whatever, and it'll display fine. It won't display the green badge or whatever. There are like things you can do to get the green badge. You can let the first request go through and then man in the middle all the other requests and put your own JavaScript or whatever on there. I think that there's going to be a talk today or tomorrow about that. by some other people, but yeah. So, okay, go for it. The question is, what are the implications for this in DNSSEC? I honestly don't know. I've been mostly ignoring DNSSEC. Right, right. This, the nice thing about this, right, is that it affects like all protocols, right? So, it's not just the web, it's your IMAP connection, your POP3 connection, your SMTP connection, or whatever. Anything that's like validating certificates in a specific way that has a SSL implementation that did it wrong, which is most of them, is vulnerable. So I don't know what DNSSEC does in terms of like checking names and stuff like that, so I'm not that equipped to answer your question. But. Yeah, yeah, cool. Yeah. Take a look at Google Chrome for the self updates. I'm going to assume that they signed them, but I guess that might be a bad assumption. So I don't know. The question was, is Google Chrome vulnerable to the auto update thing? And it's possible, hopefully they code sign them. But then the other question is like, how are the code signing certificates validated? And is it just one thing that's embedded, or do they also do this trust thing? And is it based on a name? And if it's based on a name, then the same attack might apply. So. What? Did I look into SSL VPNs? Yeah, they're vulnerable. Yeah. Do I know of certificate authorities that accept these certificates? Oh yeah, I've got the certificates. Yeah. What? I'd have to check with my lawyer. I can either confirm nor deny. I don't know. They know who they are, I think. A few years ago, I went through kind of a lot of them, and they were mostly vulnerable. Yeah, my feeling is that there are less of them now. I don't know. Sometimes it seems like by accident, a lot of them are now internally vulnerable to this thing. But yeah, you can still get them. Yeah. The question is, how realistic is this attack if you're not on the same local network as the target? The deal is, you just got to get in the middle. So if you're on a local network, it's totally easy, right? If you're not on the same local network, then you need to hijack traffic some other way. DNS cache poisoning is probably the most popular version or whatever. Yeah. So and there's also the BGP hijacking and all that stuff. If you're actually interested in doing it, it's possible, right? But it's most deadly on a LAN. I consent. Yeah. Yeah. Right. The question is, have I tried like messing with the length on the Pascal string when I pass it to the certificate authority? And that's a good idea. My feeling is that what will happen is that on the client side, when it's parsed out, because the thing is that like when the client code, like the ASN1 parsing code is parsing these things, it's doing the right thing, right? It's looking at the length, it's pulling out the right length thing that's specified and everything. It's getting all of that out, and it's totally cool, and then it's passing it as a C string to some other function, right? That just forgets that this was ASN1 and all this stuff, right? So I think that's an interesting variation, but my feeling is that you will just get the truncated value back out of the certificate. But you should try it. Yeah. Cool. What's the right way to do this? Is to just use I don't know, do the full string compare. Don't use just simple string functions to do the string compare, and include the null character in your comparison, and it will fail, right? Yeah. So store it in an actual string structure that has a length and stuff like that, and compare. If you use C++, it would probably be fine. Yeah. Other questions, comments, thoughts? Yeah, Firefox 3.5 has recently been released, and they have fixed this in Firefox 3.5. Sure, go for that. And then everyone can man in the middle that domain, rhero. Right. Cool, all right, thank you.